Hello, students. Welcome back. Now we are going to the next session in our discussion on introduction to algorithms. So first, let me move to the slide, the decide slide. So performance analysis. So as I said earlier, that the most important criteria after before and after writing an algorithm is performance analysis. So there are many criteria to judge an algorithm. Does it do what we wanted it to do? Does it work correctly? Are there documentation that describes how to use and how it works? And then are procedures created in such a way that they perform logical subfunctions? Is the code readable, etc. So as I said earlier, the two important parameters for analyzing the performance of any algorithm are space complexity and time complexity. Space complexity represents the amount of memory it needs to run to completion. Time complexity of an algorithm is the amount of computed time it needs to run to completion. So we are going to measure these two, space and time required by an algorithm. Actually, in performance measurement, we have two different concepts. That is regarding measuring, analyzing the performance of an algorithm. So we have a priori estimates and posteriori testing. So a priori analysis is after writing an algorithm, you just measure. That's an approximate measure of how much computing time and memory will be required by an algorithm. That we call it as a priori, because before implementing the algorithm, we are measuring the space and time complexities. The second one is a posteriori testing. That's performance measurement. So please keep in mind, performance evaluation has two major phases: a priori estimates, that is a performance analysis, and posteriori testing, performance measurement. So a priori estimates we measure before implementing the algorithm. Posteriori testing is actual performance measurement. We just run the algorithm with sample data sets and measure exactly how much computing time and memory is required by the algorithm. So these are the two important phases in performance evaluation. Now the first metric is space complexity. How much memory is required by the algorithm? So how do you compute, how do you evaluate the space complexity of any algorithm? Normally space complexity is computed as a sum of fixed part and the variable part. So space complexity is computed as a sum of fixed part and variable part. So what is fixed part? So this fixed part of the formula we use for computing the space complexity is independent of the characteristics of inputs and outputs. Say for example, the number and size of the inputs. So number and size of the inputs varies with different instances. Say for example, if you want to find the sum of 5 numbers, the memory requirement will be 5 memory words. So if the same program is used for computing 100 words, then we require 100 memory words. So the space required depends on the input size. But so that we consider it as the variable part. So fixed part is independent of the characteristics of the inputs and outputs. So normally the fixed part includes the instruction space. So this will be a constant. The instructions will occupy the same space for any number of input data. Whether it is used for adding 5 numbers or 10 numbers, the instruction space will be the same. And then space for simple variables and fixed size component variables. And the third one, space for constants. So these are all space come under the fixed part. So while computing space complexity, we need to distinguish between the fixed part and the variable part. So fixed part includes instruction space, space for simple variables and fixed size component variables, and space for constants. So what about the variable part? it's the opposite of the fixed part. So the space depends on the characteristics of the inputs and outputs. So it consists of the space needed by the component variables whose size is dependent on a particular problem. As I said earlier, so generating Fibonacci series up to 10 and generating Fibonacci series up to 100. So that depends. Right? Similarly, finding the sum of 5 numbers, 100 numbers or n numbers. So the value of n can be 5 or 100. So the space required by the algorithm depends on the value of n. So we consider it as a variable part. And then other reference variables and recursion stack space depend on instance characteristics. So normally the space requirement of any algorithm is given by the formula S of P. P is the algorithm, that's equal to C plus S of P. C is the constant part, the fixed part. SP is the variable part. So the space requirement based on the particular problem instance. So an example. So for this, in this particular algorithm, very simple. It involves all simple variables and constants. So how many variables are there? Totally there are 3 variables, A, B and C. Like if we assume that one word is required to store the values of each A, B and C, then the space needed by the algorithm will be 3 variables, and to store the result one more. So 4 memory words. So this 4 memory words will be the constant, will remain the same for any number of executing the same program. So there is no fixed part in this particular algorithm. So this algorithm, the simple algorithm, has only fixed part. There is no variable part. On the other hand, consider the algorithm for finding the sum of n numbers. So we have s is equal to 0.0 for I is equal to 1 to n, s is equal to s plus a of I, return s. So here totally we have n, a, I and s. So these are the 4 variables used in this program. A is the array holding the input numbers, n is the total number of total numbers, how many the number of real numbers you are going to add. S is the sum, temporary variable where you are going to store the sum. So n is an integer type, and then so the one word is required to store n, and A is a space needed by variables of type array of floating point numbers, or at least n words. So A is an array holding n numbers. So if you require one memory word for storing one number means, then it requires the size of A will be n. So here, which is the variable part? A. So the storage space of the array A depends on the value of n. So A requires 10. If the value of n is 10, it requires the storage space for A will be 100 if the value of n is 100. So here the variable part. So in this for this particular algorithm, we have variable part which is greater than or equal to n plus 3. So the space complexity of the algorithm sum is greater than or equal to n plus 3. So n memory words for storing the array A, one memory word for each n, I and s. So this is how we evaluate or compute the space complexity of any algorithm. So the another algorithm is the recursive sum. So calculating the sum of n numbers in a recursive way. So here algorithm, if you look at the algorithm recursive sum, we have 2 parameters a and n. If n is less than or equal to 0, then return 0, otherwise return. Again we are recursively calling the same algorithm, recursive sum a comma n minus 1 with a of n. So what is the space complexity of this algorithm? So while computing the space complexity, here we need to evaluate the stack space, recursion stack space. So the recursion stack space includes space for the formal parameters, the local variables, and the return address. And let us assume that the return address also requires one memory word, and then each call requires at least 3 memory words. Why? Because we require one memory word for storing the value of n, the return address, and a pointer to the array. So for each call we require 3 memory words. If here in this particular example, the depth of recursion is n plus 1. So normally if you are calling the algorithm n times, then the depth of recursion is n plus 1. So the recursion stack space needed is greater than or equal to 3 into n plus 1, because for each call we require 3 memory words multiplied by the depth of recursion n plus 1. So 3n plus 3 is the space complexity for the recursive sum algorithm. Hope you understood how to compute the space complexity. To summarize, during this session we discussed about how to compute the space complexity of any algorithm. Space complexity is computed as the sum of fixed part and the variable part. Fixed part are those memory that does not depend on the instance characteristics, but variable part depends on the instance characteristics. So we discussed 2 algorithms, one that does not involve variable part, and then 2 more algorithms, one iterative finding iterative sum, the other one is recursive sum. So both algorithms include variable part. So bye for now. Let us continue the next topic in the next session. Thank you for your listening.